Okay, now I'm doing 2006 B6, and it says an electron of mass m moving with a constant speed v, and v is much, much smaller than the speed of light. Express all algebraic answers in terms of the given quantities and fundamental constants. So they want to know, first of all, what is the Ke of the electron? That's just 1/2 mv squared. There's your m, there's your v squared, done. B says, determine the de Broglie wavelength of the electron. Well, the de Broglie wavelength is simply lambda is equal to h over p. Can't leave the p, so I'm going to rewrite that as mv because that's what momentum is, mass times velocity. All right, then it says the electron encounters a particle with the same mass and opposite charge. It's called a positron, moving with the same speed in opposite direction. Two particles undergo a head-on collision, which results in the disappearance of both particles and the production of two photons of same energy. Determine the energy of each photon. All right, well, I said, Okay, so I know that conservation of energy has to happen, so the energy before is simply equal to the kinetic energy of the electron plus Ke of the positron plus the rest mass energy Alright, so that's the energy that I had before. So that's going to be 2 1/2 mv squared, because that's the kinetic energy, and there's two of them, identical mass, velocity in the opposite direction. And then the rest mass energy is just going to be mc squared. But I have two particles that are going to provide that, so I have 2 mc squared. Okay, that's no big deal. So if this is the energy before, the energy after has to be identical. And if two photons are produced, each of those photons has to have the same amount of energy, right? Okay, but I know that this speed right here is so much smaller than the speed of light that basically each photon will have 1/2 of the 2 mc squareds, since V is much, much smaller than C. The Ke is negligible. So E for each photon is simply mc squared. Alright, that's no big deal. We can handle that. Okay, D said, determine the wavelength of each photon. Well, E is equal to HF, which can be HC over lambda. So if I want that to happen, I can say that this energy, mc squared, is equal to HC over lambda. That'll cancel. One of these will go away. So if they're asking me to find the wavelength, which they are, the wavelength is simply going to be H over mc. Alright, E says, explain why there must be 2 photons produced instead of just 1. So the momentum must be conserved, and I had the initial momentum would be 0 because I had mv plus m negative v. And that adds up to 0. Okay, and if that's true, then the only way to get 0 after the collision is to have 2 particles headed in opposite directions of equal mass. So there has to be 2 particles to provide that cancellation of the momentums. Alright, so that's good. Okay, now we're on to Form B, 2007 B7, if I didn't mess up. Alright, and it says, in the vicinity of a heavy nucleus, a high-energy photon can be converted into 2 particles, an electron and a positron. Positron, again, has the same mass as electron and equal but opposite charge. This process is called pair production. Calculate the rest energy of an electron and EVs. All right, no big deal. All right, so we want the rest energy, I think it is, in electron volts. So I said that the rest energy of an electron is simply equal to 9.11 times 10 to the minus 31st kilograms, because that's the mass of an electron. And I know that it's going to be moving at the speed of light, which is 3 times 10 to the 8th meters per second. That's an 8 right there, and that's a meters per second squared. And so when I did that much math, I said 8.2 times 10 to the minus 14th joules. And then I converted that to EVs, and when I converted it to EVs, I got 5.12 times 10 to the 5th electron volts. So that was a piece of cake. All right, B said, determine the minimum energy in electron volts that a photon must have to give rise to pair production. All right, so if I have two particles, one positron, one electron, they have the same mass, so they have the same amount of rest energy, and each photon is going to have the energy of 1, so my total energy is going to be 5.12 times 10 to the 5th electron volts for the electron, times 2 because there's a positron, so that's going to give me what, 10.24 times 10 to the 5th electron volts, but that has to be shared between two photons. So each photon is going to get 5.12 times 10 to the 5th electron volts. All right. Okay, C says calculate the wavelength of each created photon. Well, that's no big deal. So I know that energy is equal to hc over lambda, or lambda is equal to hc over E. So I put in Planck's constant. My energy is in electron volts, so I'm going to use Planck's constant in electron volts. So that was 4.14 times 10 to the minus 15th electron volts seconds times 3 times 10 to the 8th meters per second. Oops, 10 to the 8th meters per second. Sorry about that. Over my energy of 5.12 times 10 to the 5th EVs. So when I did that, I got my wavelength to be 2.42 times 10 to the minus 3 nanometers. Because I think it really comes out to be 2.42 times 10 to the minus 12 meters. Okay, so that's done. And then D as in dog says, calculate the momentum of the photon. So we have lambda equals h over p. De Broglie wavelength is equal to h over momentum. And they're asking us to find the momentum, so that's going to be p is equal to h over lambda. H was still our electron volt one. And lambda was our 2.42 times 10 to the minus 3 nanometers. So our answer comes out to be 1.71 times 10 to the minus 12th electron volt seconds per nanometer. All right. I think we have one more to do, and we'll finally be through with all these lovely nuclear physics ones. So then we had 2007, same year but a different test, B7. And it said, determine the rest energy of a positron. Well, we just did that a minute ago, but we'll do it again. So the rest energy of a positron is going to be mc squared. So it's going to be 9.11, 10 to the minus 31 kilograms, times 3 times 10 to the 8th meters per second. Got to square that little rascal. So when I did that, I got 5.1, and that came out in joules, so it was 8.2, 10 to the minus 14th joules. But that's really just 5.12 times 10 to the 5th electron volts. We did that on part A of the last one. All right, part B said, determine electron volts the energy of each emitted photon must have. So we said that was 2 times 5.12 times 10 to the 5th electron volts. But that we had 2 photons, so each of them had to have that much right there. So very similar so far. C said calculate the wavelength of each created photon. Oh my goodness. So we said, well, all right, let me stop, for I got something goofy here. I'll be right back. Alright, so let's see if we can finish this one up. So, part C is going to be identical to what we did. Part C of the last one. They want to know the magnitude of the momentum. No, I'm sorry, I lied. They want to know the wavelength. So the wavelength is going to be E equals HF. And E is equal to HC over lambda. So lambda is going to be HC over E. H is 4.14, 10 to the minus 15th electron volt seconds. C is 3 times 10 to the 8. And the energy was 5.12, 10 to the 5th EVs. So if I figured all that out, the seconds would cancel, the EVs would cancel, and I would get the wavelength to be 2.42 times 10 to the minus 3rd nanometers. Then I believe there's a part D. Part D says calculate the magnitude of the momentum, so that's going to be like part D of the one above. P is going to be H over lambda. We already got our H, because it's just a constant. 10 to the minus 3 nanometers. So if I did that correctly, I would get 1.71 times 10 to the minus 12 electron volt seconds per nanometer. And then E says, determine the total momentum of the two-photon system. Well, it has to be 0, because momentum before equals momentum after. You had a positron and an electron headed toward each other, so these photons have to pop apart in opposite directions. So it's 0. All right, here we go. Off to YouTube.